And our next talk is by Dana Azouri and Itai Mayroz from Tel Aviv University. And they will talk, it's a short talk. They will talk about a tree reconstruction game, phylogenetic reconstruction using reinforcement learning. So I believe this is Dana who is going to talk to us. Dana, the floor is yours.
Yes. So hi everyone, I'm Dana. I'm a PhD student at Itai Mayroz and Tal Pupko's lab. And I'm here today to present our ideas of combining the two words of AI and phylogenomics. When we talk about phylogenetic inferences, we are looking at core and day lineages. And our data is the alignment of the sequences we are interested in. Based on the sequence data we have, we produce a phylogenetic tree, which is our hypothesis regarding the evolutionary relations between the species. Here, for example, there are 3 species, and here is the inferred phylogeny for them. But how do we know that this is the tree for these species? Because we assessed all other alternatives. Here, chimpanzee and human are grouped together, and here gorilla and chimpanzee are grouped together, and we can also group together human and gorilla. So this tree, received the highest score. That's why we say, that this is the phylogeny for this species. So here, there are only 3 options for possible phylogenies. But the number of alternatives grows super exponentially with the number of species in the alignment we are interested in. So normally, we need to search in a huge space of possible trees, and thus finding the tree that best describes our set of sequences is hard. In fact, it is an NP-hard problem, so this is not a feasible task. In practice, the current methods for phylogeny reconstruction use heuristics, so the optimal tree for the data is not guaranteed. In a bit more details, when we go over the large tree space, we must evaluate each tree. The likelihood functions, we want to calculate the likelihood function that scores the fit to the data. Based on the evolutionary model we use. And this procedure is very time consuming on itself because it is an iterative process in which we iterate over candidate trees and evaluate the likelihoods. And the process ends only when we can find a tree with better score anymore. So how do we move in the tree space from one tree to another to explore the trees? We need to first generate the search by building a single tree that will be our starting point for the search. Then we need to be able to move in the space to reach neighboring trees. But what is a neighboring tree at the first place? So a heuristic technique for to move between neighboring trees, we can define it as all the trees that we can move to by cutting a certain edge and regrafting it to another edge in the tree, in the remaining subtree. Okay, so that was an example of moving from this tree to a neighbor tree following this specific cut and paste, okay? But we can actually regraph the prune branch also to any other remaining branches. And in order to consider all neighbors of this small tree, we must consider all pairs of cut and paste. So there are many, and so on, okay? So, sorry. But we got the idea, like we have plenty of neighboring trees, and we want to evaluate in each move within the enormous tree space. So we use various heuristics to make the task feasible. But when we include heuristics in the game, it comes at the cost of our chances to get an accurate result. So it is clear our challenge now is the existing trade-off between accuracy and feasibility. What we propose is to let the machine learn what is the best way to explore the tree space instead of just guessing the heuristics. So in order to do this, I began with reconstructing a single starting tree. And then I obtained all its possible single-step neighbors. And I performed this to each of the thousands of empirical data sets we assembled. So my training data is millions, dozens of millions of samples. And for each sample, I extracted a few dozens of simple features that we have found them to be informative attributes of the data, such as the tree size or the length of the branches that are being changed when we perform a move. And for the length stage, I also computed the change in the likelihood score for each move. And this is the value I aim to predict. So I harnessed a machine learning algorithm named random forest and trained a model that learns the mapping between the features and our score. So now the trained model can predict the change in likelihood without explicitly calculating the likelihood function. And this could be beneficial for sure, because it's in this way, if we succeed, we can rapidly rank the neighboring trees. But now we must ask, is this fast ranking procedure also accurate? In other words, how accurate are the predictions when we apply the model on unseen data? So in order to assess the model's performance, I applied it on a single tree. So I could evaluate the correlation between the real rankings on the x-axis that we would have observed if we explicitly calculated the likelihood, and the rankings that our model predicted here in the y-axis. And we can immediately notice that these are highly correlated. But I then wanted to evaluate the same correlation metric based on thousands of different data sets. So I have a distribution of correlations, and we can see it resulted in high correlation for the majority of data sets. So we can conclude from that and say that since the trained model rapidly and accurately predicts the benefit of each move, the learning approach boosts the tree search algorithms, the maximum likelihood algorithms, without compromising accuracy. Okay, so as we all know here, research is conducted in small steps. So until recently, we focused on a single step at a time to demonstrate proof of concept. And by this, we validated our thesis that we ever get a signal from the data.
Dana, 1 minute for the question session.
Okay, so I tried to search the whole space using a more advanced AI technique. Specifically, it's a reinforcement learning technique. And I'll just skip. I want to say that reinforcement learning in general is an approach that tends to be geared around games, because in reinforcement learning, the machine learns through trial and error, and the key is the practice. So it can gain a lot more experience than any human being can have time or patience to. So we chose specifically reinforcement learning because we have many exciting or successful examples of reinforcement learning. I don't know if any of you are familiar with the game Go. AlphaGo, the machine of Google, wasn't familiar with the game rules itself, but the machine could beat the world champion. We showed that a machine learning model is able to efficiently predict the moves that improve the likelihood score. And that also might allow in the future the use of more complex and realistic evolutionary models, and potentially will improve the accuracy of evolutionary inferences in the future.
Thank you, Dana.
Sure.
Very nice. Do we have questions for Dana?
How is the accuracy of the machine learning ranking measured?
So we have few accuracy metrics. One of them is the Spearman correlation I showed. Okay, between all, I'm taking one tree, generating all its neighbors, and the Spearman correlation is between the delta likelihood, the real delta likelihood to my predictions. So it's the correlation. We also measure some metrics of the best tree, like the best empirical tree, what was our prediction, and vice versa, like some measures that I say like the 5 top percent of my predictions are the most probable to include the best likelihood, like the best empirical likelihood. So we go further with it, but I showed here only the Spearman correlation.
Thank you very much.